In this example, we're being given a circuit that contains a few elements. For example, it contains a resistor in here, a resistor in here, and a capacitor and an inductor in here. And we're being asked to compute what the voltage across that capacitor is V of t, which I can also call Vc of t. We're also being given that there's an initial current flowing through this inductor in this particular direction, and that's exactly 0.5 amp. And the voltage initially across that capacitor is 1 volt. So they both store some initial energy at the beginning. And you might have recognized that this 8 and the 10 are neither in parallel nor in series, and we can't combine. These two are in parallel, but we can't combine them. These two are in series, but we can't combine them. So we need to write a differential equation that describes the circuit as it is. And as it turns out, it's not as straightforward as others, or as a simple parallel RLC or a series RLC. So it's going to be, well, we can analyze it like a normal circuit. It's just going to be, the equations we'll come up with will contain some sort of derivatives. All right, so let me start off by saying, let's write the KVL equation on this circuit across in here. Okay, so this is the KVL equation. Let's do that, and I'm going to just call it 1. Okay, so what I will do is I'll say, okay, let's assume that the voltage across that capacitor, that inductor, is actually plus and minus in here. This is plus and minus in here, and this is plus and minus in here, just to make things a little bit easier. So what do we have? Well, we have the voltage across the inductor. So this here is VL of t. Okay, so VL of t plus, well, this here is I of t, or IL of t. Okay, I can call it IL of t since it's the current flowing through the inductor. That is 10 times IL of t, that's Ohm's law, plus, well, we can definitely, this is VC or VT, I'll just call it VC of t for now, okay, and that equals 0. Of course, I cannot say it's I times I of t because the I is not the same anymore. It actually splits in here, and actually we're going to use that fact to write KCL in here. Anyhow, if you think about it, we have a VC, an ILL, and V of L. I think it's a little bit easier just to deal with either the currents or voltages for the capacitor and the currents or voltages for the inductor. So what I will do is I'll rewrite this one here in terms of I of L, so I reduce the number of variables slightly. So, well, let's do that. So we'll know that this one here is typically L times di of L of t. Okay, let me just write it here, IL of t divided by d of t. All right, and based on passive sign convention, the current is flowing to the positive, so positive is okay. And the value of L in this particular case happened to be 2, so I'll just substitute it, that's 2, plus 10 IL of t plus VC of t equals 0. So this one here, I'm just going to call it 1. It contains VC of t and IL of t, so it basically relates the IL and the VC together. So we need to write another equation in here, and that equation is here. So what I will do is I'll go in here and I write a KCL equation for this. Well, KCL tells me the following. Well, here I have IL of t in here, okay, and I'll tell you that let's call this here IC of t, and this one here I'll basically just keep it VC of t or something like that, okay. Yeah, we'll keep it, well, we can just call it I8 of t if you wanted to. That's fine. All right, so let's write the KCL equation. So this one here is KVL at 1, and now we're going to write KCL. So what does KCL tells me? IL of t is just simply IC of t plus I8 of t. All right, but what is IL of t? Well, IL of t, I don't need to rewrite it because it's somewhere here. Actually, I'm looking for it. If you think about it, if I can get rid of IL of t and IL of t in here and I'll write it in terms of VC of t, I'll be golden because I'll end up with an equation that contains VC of t. So my task now is to basically convert everything here in terms of VC of t. All right, so, well, that's simple for the first one, IC of t. I know that this is simply C times dVC of t divided by d of t, because this is the current flowing through a capacitor, so it's C times dV divided by dt. Good, so that is in terms of VC of t. All right, but what is the value of C? Well, we can substitute it by just simply 1 divided by 8 farads, because that's the value. Okay, what about the I8 of t? Well, can I write it in terms of VC of t? That's I of t. Yes, we can. It's actually, I know the voltage across the resistor is VC of t, so I can just simply say that is, I believe, 1 divided by 8 VC of t. Okay, so that's actually convenient. So IL of t, and I'm just going to call it 2. So what I can do is I can do the following. I can just take this I of t in here, okay, and substitute it in here. So I'll have everything in terms of VC. But what about this one here? Well, this one is based on the derivative or the first derivative of the IL of t. So what I'll do is I'll tell you, okay, let's take the first derivative. So the first derivative of IL of t divided by d of t is just simply 1 divided by 8 dvc of t. That's the second derivative, plus 1 divided by 8 of the first derivative in here. Okay, this is plus vc of t divided by d of t. Alright, so what I'll do is I'll take 2 and 3 and substitute in 1. That's what I'll do. So what I'll have is the following. What is 2 times 1 divided by 8 dvc of t divided by d of t? Actually, it's this one here. It's actually the second derivative. Alright, so d squared vc of t divided by dt squared plus 1 divided by, actually let's take that here out. I don't need it. Okay, and we do this one here. Okay, and that becomes dvc of t divided by d of t. Alright, so this here I just substituted this guy. So now we do that. 10 times what? Also divided by 8 dvc of t divided by d of t plus vc of t, plus that leaves me this vc of t in here. Vc of t equals 0. And if you take a look here, all we have to do is a little bit of algebra, and we will end up with a second order differential equations for vc of t, and that is here. d squared vc of t divided by dt squared plus 6 dvc of t divided by d of t plus 9 vc of t equals 0. And this is just a normal second order differential equation. And frankly speaking, if you take a look at this here, it's actually a homogeneous one, so it doesn't even have a particular solution. So it's just a complementary solution. All right, we can find the complementary solution like we have been finding these for any circuit. So all we have to do is just take the characteristic equation. That will be 6s squared, 6 of s plus 9 of s equals 0. So we can say, well, 2 of alpha is just simply 6. That means alpha is just 3. Omega 0 squared is 9. That means omega 0 is the square root of 9 with the 3. That tells me that alpha is equal to omega 0. That means it is critically damped. Okay, so critically damped, and of course you can compute what the discriminant is, and you should end up with 0. So what do? Well, we take a look at our notes and we find out that the solution should be of the following form. So this is Vc of t, or V of t is a particular solution, which is 0 in our case. So all we have to do is just figure out what the complementary solution. The complementary solution is k1 e to the power of s of t. Actually, s in this particular case is negative alpha t plus k2 t e to the negative alpha t. So let's substitute k1 e to the negative 2, or actually 3 of t plus k2 t e to the negative 3 of t, and that's vc of t. So that is the equation, but it's still missing a couple of things, which is these two constants. So if I take a look at the original circuit in here, just to see what we have. So in the original circuit, we have some sort of initial values and initial voltages and currents, so let me just use them. So here's the circuit. So we're going to be using a couple of initial conditions, that's that and this, to figure out what the k1 and k2. So simply we can say Vc at 0 is just simply k1 e to the power 0 and k2 is just 0. So what is Vc of 0? Do we know it? It's the voltage across the capacitor, and we do know that it's 1. That means k1 is just simply 1. How about if we say dvc of t divided by d of t? Well, we should know that this is simply the voltage across the capacitor, so it's 1 divided by c times I c of t. Okay, all right, but what is IC of t? Well, we have to figure out what these voltages and currents are, so let's compute them. So do we know this one here? I'm going to call it IL of 0. We do, and that's 0.5. Do we know the initial current in here? That's basically I8 of 0. Technically we know, because we know the voltage across it. The voltage is 1, so it's 8 divided by 1, right? Yes. it is 8 divided by 1. Actually, it's 1 divided by 8, not 8 divided by 1, because it's 1 volt and it's 8 ohms. So it's 1 divided by 8. Do we know that here? That's actually what we're looking for. This is IC0. That's what I'm after actually eventually, because what I'm after is the following. I want this here to be t equals 0, and this one here will be 0. That's what I'm after. All right, so let's compute it in here. What we have is IL of 0 is just simply IC of 0, which I'm looking for, plus 1 divided by 8. But I know that IL of 0 is just simply 0.5. Okay, so now we know what IC of 0 is, and that IC of 0 is just 0.5 minus 1 divided by 8. And that is, I believe, 0.375 amps. Okay, so now we can use it. We can just say dVc of t divided by d of t evaluated at t equals 0 is just simply 1 divided by c, which is 1 divided by 8 times 0.375. And that is equal to exactly 3. So we know now dVc of t divided by dt evaluated at t equals 0 is just simply 3. But if you take a look at the notes, we know for a critically damped, this is also equal to negative alpha k1 plus k2. Well, that means 3 equals negative alpha. Well, we know what alpha is. I believe it's a 3, yes. And we know that k1 is just simply 1 plus k2. That means k2 is just simply 6. So now we substitute the k1 and k2. What we'll end up with is Vc of t is just k1, which is 1 e to the negative 3 of t, plus k2, which is 6 t e to the negative 3 of t. And that's here is volt for t is greater than or equal to 0. So that is actually the solution that we're looking for. And it's critically damped, so if you take a look at the plot, this is how it should look like. So initially what we have is the voltage across it is 1 volt, and what it does, it shoots up and then it goes down to the final value, which is 0. And it makes sense that the final value is 0 because whatever energy is stored in the inductor or the capacitor will be consumed by these two resistors, so that will be 0. And that's exactly what we have in here, e to the negative 3t plus c 6t times e to the negative 3t.